Okay, so welcome back, everybody. So we have a couple more topics to cover. One of the last ones is actually something that if you've had Math 240 or Math 246, sorry, not Math 240, Math 246 or Math 243 previously, then you will have seen some of this. But maybe it won't be clear the way that I'm going to formulate this in what way you've seen it. But the first thing that I'm going to talk about is an application to a discretized PDE. Now, the overarching thing that we're going to do here is think of applications of linear algebra to differential equations. Now, of course, the end, like the last like 30%, we'll say, of a differential equations course, that is Math 246, Math 243, deals with systems, first order systems of differential equations. So, and that necessarily involves some linear algebra, eigenvalues, eigenvectors, matrix exponentials, which we are going to talk about. So this is a little bit of a rehash of some of that stuff, but maybe to show you another angle here, rather than simply starting out with a system of first order differential equations just right out of the gate, I'm going to show you how maybe a thing you haven't considered before can be turned into essentially that. So what we're going to start out with is a classical um, one-dimensional heat equation. Now, this is, you could also consider this the diffusion equation. It's just here the thing being diffused is heat. So what is the 1D heat equation? The idea is that we have a function that is a function of both x and t. Here, t is time, x is going to be the position. 1D, this is going to be a thin metal rod. Okay, that has ends. So we have endpoints here. This is our rod. X is going to be where we are along the rod. T is time. Now we are going to have boundary conditions, or BCs, here. All right, like this, BCs. Maybe we could start with some like Dirichlet boundary conditions. So something like this, U equals 0 at the ends. Here, this is my temperature. And of course, I mean temperature at the ordered pair xt, so x is the position on this thin metal rod, and t is the time. What is the heat equation itself, or the one-dimensional diffusion equation? It is the partial derivative of u with respect to t is equal to the second order partial of u with respect to x. Now, oftentimes there will be a constant here. I'm just going to have that constant be 1 in this case. This is called the heat equation in 1D. You might notice that we're in 1D here, so you can't really tell what's going on here. But if this were in like 3D, what is happening here is this is actually the Laplacian of the thing. If you don't remember what the Laplacian is, it's the trace of the Hessian matrix. So if Hessian matrix contains all the mixed second order partials of a function of several space variables here, the Hessian is, yeah, it's all the mixed second order partials. The trace of the Hessian is going to be the sum of the pure second order terms. So it's going to be uh, uh, you know u sub xx plus u sub yy plus u sub zz. Here, notice that the second order partials we're talking about are only with respect to the space variable, because we have a space variable and a time variable here. Now, I'm not going to get the reason I went through that pretty fast. If you're confused, if you haven't seen this before, what I'm doing here is we're not actually going to study this, because this is an example of a partial differential equation. And the thing about partial differential equations is that it might kind of sort of seem like, well, for instance, right, going from Calc 1 and Calc 2 to like Calc 3. right? The way that you proceed from one variable to several variables, not a big deal in a way, right? Maybe if you really hated Calc 3, you would fight that assertion, but not really that big of a deal going from one variable to several variables. In terms of how things generalize, a lot of it is straightforward, right? And it intuitively follows. So you might think that that's kind of how ODE to PDE goes. There are some aspects of like you need some ODE theory to do some of the PDE stuff, but it doesn't really proceed in the same way. PDE is kind of its own thing, and it has a distinctly different flavor from ODE in a lot of ways. So it is its own thing. If you are interested in studying equations like this from that angle, I have actually a Math 462 playlist on YouTube that you can watch. It's a pretty hardcore, pretty sophisticated treatment of it in terms of for an undergrad course in PDE. It's pretty fast paced, pretty dense. But if you want to have a look at it, you can see this fully described from in the language of PDE. But we're not going to do that, okay? We're not going to do that. So what we are going to do instead, I've mentioned that we have these boundary conditions. So at each endpoint, we're going to have boundary conditions u equals 0. And what I'm going to do is I'm going to discretize this. And my first way of doing this is to, rather than viewing this as one continuous bar, I'm going to split it into two pieces. Now I could split it into more pieces, but just to get this process started, I'm going to begin with two. I'm going to split it into two pieces, and I'm going to take those two pieces and label the temperatures on those U1 and U2. So that here, if I'm splitting it into n pieces, n is equal to 2 in this way. Okay. Now, what is the principle here? The main principle is that the rate at which heat flows across a boundary. So what is a boundary here, right? So there's the two ends. But now, splitting this into two pieces, we've created another boundary here between the two halves, right, between the two pieces. Okay, and so what's the principle? The principle is that the rate at which heat flows across a boundary is proportional to the temperature difference of the two regions at the boundary. Okay, so to make this simpler, we're just going to assume that they are equal rather than being proportional in this way. So we're going to assume that this rate is equal to the temperature difference. So it's proportional, and we're going to take the constant to be 1. So for example, heat might leave the left endpoint of the first region at a rate of U1T, and it leaves the right endpoint at a rate of U1 minus U2 of T, which gives us this differential equation, if you like, from what I just described there. I'm gonna draw the same picture over again. So that principle that I just described gives rise to the differential equation, right? Because this is my heat flow rate, right? Differentiating in this way with respect to time. This is going to be minus U1 of T minus U1 of T minus U2 of T, which is minus 2 U1 of T plus U2. So that's what I get from that relationship. And you can note that we had to include negative signs here because we're discussing the rate at which heat was leaving the first region. Okay, so that's why we have minus signs here. We assume that the temperature is 0. That's fixed at the ends. You can think about, like this being a region outside of the rod, if you like. And so heat is flowing out of the rod into the outside, but it's not raising the temperature outside. So we can think of everything and this outside region having temperature 0, okay, if you like. Because remember, this is a 1D thing, so it's okay if the physical intuition's a little off here because this is a one-dimensional, right? It doesn't have a thickness. You're thinking of this as being a very thin rod. Okay, so in a similar way, we can consider how heat enters and leaves the second region. So what's going on there? So it flows out the right of the second region at a rate of U2 of t, and it flows in from the first region at a rate of U1 minus U2, right? So not proportional to it, but U1 minus U2. We're taking that proportionality constant to be 1. So what do I get there? I get another differential equation, U2 prime, which is minus, or it's going to be, sorry, U1 of t minus U2 of t minus U2 of t. So this is going to be U1 of t minus 2 U2 of t. So putting this together, this is actually a system of first order differential equations that looks like this. This is U1, putting them together, U1 prime of t is minus 2 U1 of t plus U2 of t, and U2 prime of t is U1 of t minus 2 U2 of t. And now, of course, rather than write it as a system in this fashion, I can write a vector valued function u having component functions U1 of t and U2 of t, which then allows me to write this as a matrix equation. I can put this in matrix form here, so that what I get is that this system becomes U1 prime is equal to the matrix minus 2, 1, 1, minus 2 times u. All right. If you like, I'm suppressing the t notation here, but if you like, I don't have to. There we go. So now I have rewritten this system of differential equations, put it in matrix form. You might remember this again from differential equations. If you've had Math 246 or 243, you know exactly how this goes. Now, it turns out that in order to get a unique solution out of this, I need to specify what is called an initial condition. So an initial condition could be specified at any time I'm calling my initial time. It doesn't have to be 0, but frequently it is 0. So what I need is an initial vector, right? So I can choose, whatever you like here. So for instance, let's choose 10 and 0. So this would imply that U1 of 0 is 10 and U2 of 0 is 0. Now, this is just an example. I didn't get these numbers from the problem anywhere. I just chose this, right? So the matrix differential equation and this initial condition taken together are called an IVP, which is an initial value problem. Now, this terminology applies even for just regular old ordinary differential equations. So this is frequently when you take a differential equations course, when you are asked to find a unique solution, typically the context that you're asked to find it is you're solving an IVP. So there's a variety of what are called existence and uniqueness theorems for ODEs that guarantee, with pretty lax requirements, the existence and uniqueness of a solution to a given IVP. But it is very important that the initial condition be satisfied be specified, because if it is not, in general, a differential equation has infinitely many solutions. Okay, that's just how it goes. All right, so what is the deal here? When we solve this, we will get functions, U1 and U2, that should tell us exactly how the heat is flowing in the bar, in each of their regions of the bar. Intuitively, you'd expect heat to flow out of the first region into the second, but also out the endpoints, right? And eventually, of course, all of the heat should leave the rod. It should diffuse through the rod and leave the rod eventually. Okay. Rather than going ahead and starting on how to solve this, let's see what happens if we do. Let's repeat the same process, but now instead of splitting this up into two pieces, let's say I split it up into four pieces. So let's let's let n equals 4 here. So let's have the exact same bar description. So we have u equals 0 at the endpoints. This is our boundary conditions. But then let's have these splits and see how this would work if we were splitting it into four pieces instead. So here, heat is going to leave the rod, but it's only going to leave the rod from region 1 or region 4. So it's going to leave at this end or that end, but otherwise it's going to go between the regions, right? So it can still only leave via the endpoints here. Following the exact same pattern here, the resulting system of differential equations now is going to involve four unknown functions, u1 to u4, and their derivatives. So the first one would be u1 prime, would be, again, following the same reasoning, this would be minus 2 u1t plus u2 of t. u2 of prime, u2 prime would be u1 of t minus 2 u2 of t plus u3 of t. Again, now, right, we have another place that heat is flowing into, right, from region 2. It's coming from region 1 into region 2, between region 2 and 3. So this is what we get. Here, use 3 prime of t. This is u2 of t. Region 3 doesn't touch region 1, so I don't have to worry about region 1 here. That's the interpretation. So this would be u2 of t minus 2 u3 of t plus u4 of t. And one more, u sub 4 prime of t would be, again, u sub 4 only it's going out one end, and then region 3 is the only other region that gets touched here, so this would be u sub 3 of t minus 2 u sub 4 of t. So this description explains what's happening in this bar. Now we would let our u of t be a vector that has four component functions here, u1, u2, u3, and u4. Then what we obtain here is that u prime of t is equal to, now I'm writing out this matrix here, just reading row-wise. This would be, so that's reading equation by equation here. This would be minus 2, 1, 0, 0. Next would be 1, minus 2, 1, 0. Next would be 0, 1, minus 2, 1, and 0, 0, 1, 2. Sorry, minus 2 times u of t. And an initial condition, of course, would be specifying initial values for each of these four functions. Okay, so now we've understood how to set up this problem in a way that involves a matrix. Now, because you're solving a differential equation, when you're solving a differential equation, ultimately you're solving for an unknown function. If we pay attention to this, right, let's zoom out for a second. These are placeholders, right? U is unknown. I don't know what U is. The derivative of U obviously is unknown in the sense that U is unknown. I'm solving for U. So in this setup of both of these types of problems that I just did, the only thing that I actually know here is the matrix. So in a sense, this matrix has to, if you believe that I can solve this with the info that I've been given plus an initial condition, then this matrix somehow has to determine that solution, right? There's like if I'm able to solve it based on nothing but this matrix is kind of the only thing here. So this matrix somehow has to determine the solution. So how does that work? Now, if you have had Math 246 or Math 243, then you're screaming at your screen right now because you already know how this works. Okay, which is we solve with matrix exponentials. What are matrix exponentials? Well, before we get into that, let's do our generic setup. So what is the setup? We have a differential equation that involves solving for a vector of unknown functions. We'll call them x1 to xn. So these are all unknown functions. Okay. We would like to solve this matrix differential equation x prime equals a times x with initial condition x of 0 is equal to a naught. So this is now an IVP. By a theorem that I'm not going to state, we'll call it an existence and uniqueness theorem for systems of differential equations, first order differential equations. We do in fact get a unique solution here. So there does exist a unique solution for the system. So now we just need to find it. What is the idea? When n is equal to 1, this is not a vector valued function. This is a scalar valued function since it's a vector with one component, so it's a scalar. So this is just an ODE of a very simple type, which is x prime ax, where I have just a plain old initial condition here. This A is now a 1 by 1 matrix instead of being an n by n matrix like this A. Right. So that this is function, the derivative of function is equal to A times function itself. What solves this? Well, it turns out that, of course, we know what the solution is here. E to the AT does it. But, of course, this isn't the most general form this takes, right? So this is but one form. What's the general solution? That is the form any solution has to take here. The general solution is a constant times e to the AT. Any solution to this differential equation will be of this form. Once you specify an initial condition, you can plug in that initial condition to impose a value for that constant c. Okay, so this constant c is determined by plugging in that initial condition. This is how differential equations work. Okay, so let's use this, going back to this differential equation. The idea is that the solution is this thing. Maybe I should say here, when I impose this initial condition, I plug in 0. This is 1 and this becomes x naught, so the unique solution, once I impose this, is e to the AT times the number x naught. I'm doing this for a reason, because here my idea is that the solution to this should be e to the AT, if you like to call it that, times the vector x naught. Done. There's only one problem here. There's absolutely no question what e to the AT means, where a is a scalar valued thing. You know what that means. And then I'm multiplying this by vector. But what is this? Only one problem. What does that mean? Now, there's a whole lot that goes into explaining this conceptually when you take a differential equations course. We're not going to do that. Okay, we're focusing on the linear algebra aspect of this, and we're going to we're going to shortcut this and think about what this actually is. So recall, if you were like forced by someone to give a definition of what e to the x is, problem is you have to define what the base of the natural logarithm is or whatever, and that's kind of annoying, but there's a much better way of describing what e to the x is. E to the x is simply this very nice series. It is the sum from k equals 0 to infinity of x to the k over k factorial. Right? The nicest possible Taylor series thing you've ever seen in your life. Right? And the only non-trivial function that is its own derivative. You can see that directly from this series, which is, of course, the Taylor series for e to the x. Okay, this actually converges for every number x, so it has infinite radius of convergence. So this is all we need for e to the x. Super nice. So then what's my definition for, we'll say, the matrix version of this? If A is an n by n matrix, what is e to the a? What if I just plug A in formally to this series? So now we have matrix powers here. What is that? Instead of 1 here, this is going to be the n by n identity matrix plus a squared over 2, right? So 1/2 a squared plus 1/6 a cubed, and so on. What if we do that here? Well, does this work? We have a theorem immediately pops out of this, because you might have a question using an infinite series like this to define this matrix thing. You have a question about convergence. Here there was no question at all, because this is like one of the first series. It's one of the first power series you ever proved convergence for, right? And compute the radius of convergence to be infinite. Here the question about convergence might come up. This theorem says this thing converges. So if A n by n matrix, e to the a converges, i.e. e to the a is defined for all n by n matrices. Okay, but is this going to be the same matrix exponential object that we just tried to use? Right, you can check. Here's an example. Check, for instance, that e to the n by n zero matrix is in fact the n by n identity. I'm not going to write that out. This is for you to check, okay, that this works. So directly from this, what's super nice is, okay, this is how the exponential works. Okay, what else do we get that shows us that we're on the right path? If we, for instance, try to take the derivative with respect to t of e to the at, what do I get? This is a e to the at. Okay. I'm not going to prove this, but you can quickly do it using the definition. The proof is actually the same as it is showing that the derivative of e to the x is e to the x. Okay, or the derivative of e to the ax is a e to the ax. Okay. And so, the thing that we're actually interested in, A is an n by n matrix. Consider this differential equation with initial condition. The unique solution to the IVP is x of t is typically, even though this would also make sense typically for some reasons, this is the notation that we use. We write the t first because it's like a scalar multiplying the matrix. Whatever, it's not a big deal. But just to be consistent, this is also how the notation that's used in Math 246 and Math 243. So I will stick to this. This is e to the ta times that initial vector, x naught, and we're done. That's it. That's how to solve that. So those two, that discussion we had about splitting the thin metal bar up into pieces and then coming up with a system of first order differential equations to describe that situation, we could solve that now if only we know how to find this matrix exponential. We have shown that this thing we've defined to be the matrix exponential is in fact what we want, if you believe this theorem. Okay, but here's the question. How do I actually find this matrix exponential? Because the problem is that, look at how I define this thing. How do I define this? Okay, say I give you a matrix. Say I give you a 3 by 3 matrix. What is e to the a? This has infinitely many terms in it, right? So you're taking a limit here necessarily. Like that seems really, really nasty. Even if you know this converges for like conceptual reasons, actually figuring out what this is seems really, really nasty. So how the hell do you do that? The answer, what are called the typical way that you learn to do this, and maybe the quickest and dirtiest way, is the eigenmethod approach. This is how you learn to do it in Math 243, Math 246. This is what you are likely familiar with if you've had a differential equations course before. Alternatively, included as part of this, if it's relevant, is diagonalization of said matrix. It turns out that ultimately what completely determines the matrix exponential are its eigenvalues and eigenvectors. Okay, so if you are in the nice case that the matrix in question is actually diagonalizable, you really get something nice out of it, and it's a lot easier to deal with. Okay, and so here's the idea. E to the d is easy to find if d is diagonal. Now we know what a diagonal matrix is. So a diagonal matrix D looks like this. Where everything is zero except possibly what is on its diagonal is not zero. Now, these could also be zero. So for instance, the zero matrix is in fact an example of a diagonal matrix. Okay, but everything off the diagonal has to be zero. This is an example of a diagonal matrix. Then e to the d is actually just this. It's what you hope and dream it is, right? When you first envision a matrix exponential. This is the only case where it looks like this, where it's this easy. Okay, typically it's going to be a lot nastier than that. I'm not going to prove why this is. This can actually be done directly from the definition of matrix exponential. What does it mean if A is diagonalizable? Just recall quickly from linear algebra. If rather than walk you through this, maybe what I'll do is just say go back and watch the first two lecture videos of this course where I did a big long review of like all of linear algebra essentially. So A is diagonalizable means that A is similar to a diagonal matrix. I'll write it like this. I'll use tilde to denote similarity. So A is similar to a diagonal matrix D. But what that means is that A is equal to P d P inverse, where P is invertible. As I mentioned before, this is also, we could also say that A and D are conjugate, or they belong to the same conjugacy class. One of the whole points, and I mentioned this in those first two lectures, so I'm not going to go over this again. So quick theorem, if A is diagonalizable, which means A is equal to P dP inverse, then E to the A is equal to P E to the D P inverse. And this is key, okay? Because E to the D is easy to find, right? So putting those together, this means that if A is P dP inverse, and D is the diagonal matrix containing, say, the eigenvalues of A, if A is in fact diagonalizable, this is how it works, possibly listed with multiplicities, right? Then E to the A is whatever P is. How do you construct P if A is diagonalizable? P consists of the n linearly independent eigenvectors that you get from diagonalizing A. So you find all the eigenvalues of A, you find all the associated eigenvectors, that is, you find the dimensions of each of the corresponding eigenspaces. The dimension count will work out in the event that A is diagonalizable. The dimension count will work out so that you will get enough linearly independent eigenvectors to fill out an n by n matrix P. Necessarily, it's going to be invertible because the eigenvectors are linearly independent. So this is going to be E to the D P inverse, but E to the D is very easy to compute here. It's just this, right? So let's go back and apply this to our problem. Back to our example. How did this actually work? Let's write out our example nicely here. So we have u prime of t is equal to, this is our 2 by 2 matrix here, minus 2, 1, 1, minus 2 times u. With initial vector, I think we chose 10, 0 as our, this wasn't present in the problem, we just picked this to be our initial temperature distribution. Accordingly, solution u of t is given by e to the ta times this vector 10, 0, where A is this matrix. All right, so A is that matrix. Well, what are the eigenvalues of A? Well, it has two eigenvalues, minus 1 and minus 3. So lambda 1, we'll say minus 1, has corresponding eigenvector v1, which is 1, 1. And eigenvalue lambda 2, which is minus 3, has corresponding eigenvector 1, minus 1. I have two distinct eigenvalues. Necessarily, I have two linearly independent eigenvectors, so that P is the matrix that contains those eigenvectors as its columns. If I'm choosing that as my order for the columns, then D, I have to choose the eigenvalues to go in the right order to match this P. You can do it either way, whatever. So here, for D, this would be, since I put 1, 1 here, this would be minus 1, 0, 0, minus 3. So that A is P D P inverse. If I actually wrote this out, if you wanted to really check yourself what this is, P here is 1, 1, 1, minus 1. D is minus 1, 0, 0, minus 3. P inverse is a 2 by 2, so writing out its inverse explicitly is easy. This is 1 half, 1 half, 1 half, minus 1 half. Okay, so then what is e to the ta? put this here. What is this thing? This is P e to the TD P inverse, which is, I'm just writing out these matrices again. This is 1, 1, 1, minus 1. E to the TD, of course, is E to the T, 0, 0, e to the minus T, E to the minus 3T. Here we go. Times 1 half, 1 half, 1 half, minus 1 half. Multiplying this out, what do I get? I get, this is going to be a 2 by 2. Multiplying this out, this is 1 half e to the minus t plus 1 half e to the minus 3t. This next entry is going to be 1 half e to the minus t minus 1 half e to the minus 3t. Next entry is 1 half e to the minus t minus 1 half e to the minus 3t. And the last entry is 1 half e to the minus t plus 1 half e to the minus 3t. Okay, you can just check that is indeed what we get. So that now my u of t supposedly is e to the ta times my initial vector 10, 0. Doing that multiplication out, what I get is the 2 by 1 vector 5 e to the minus t plus 5 e to the minus 3t and 5 e to the minus t minus 5 e to the minus 3t. You can check that the initial condition works, right? Plug in t equals 0, I get 5 plus 5, 5 minus 5, so 10 and 0. Okay, that works. But also this solves the differential equation. And so what this tells you is that, going back to that original problem, u1 of t, the function that governs the temperature in the first region of that bar, is 5e to the minus t plus 5e to the minus 3t. And u2, which governs the temperature in the second region of the bar, is 5e to the minus t minus 5e to the minus 3t. So this gives us a complete description here of the temperature on the two regions of the rod as time goes on, right? So for instance, u of 0 is our initial temperature distribution. So the temperature is 10 in the first region, 0 in the second region. So then at time like 0.25, what do I get? This is like approximately, so we'll plug this in here. This is like 6.26, 1.53. What about at like 0.5? This is approximately 4.15, 1.92. What about like 0.75? This is approximately 2.89, 1.83. And think in your head, does this seem to be matching intuitively how the temperature would change in that bar? This is now 2.09, 1.59, right? We expect, of course, these to both go to 0 as t goes to infinity, but like, are they matching what you expect should be happening here? Forget about the time units, right? That's, we can mess with the numbers in a way that maybe that would make sense. You might view this as being a very, very fast process, but you know, does this match your intuition for how heat flow or diffusion would actually work here? And the answer is yeah, this seems to actually be working. Because remember, in our original setup, we only had two regions, and so for both region, you have heat flowing between the regions and also out leaving the bar out the ends. So this does seem to, in fact, be modeling what it is that's going on here. Okay. So that is that. I think this is a pretty quick and dirty explanation for how matrix exponentials work and how they come in. People that have taken Math 243, Math 246 might feel shortchanged by saying, wow, why did we spend so much time on that in 243 and 246? And well, the answer is, I mean, it warrants spending more time on it. Maybe this was a little bit too fast, but having a bunch of linear algebra before you encounter that, which is not a prereq for Math 243 or 246, I might add. In fact, that's the point of Math 243, is that 240 is not a prereq for it. You get to shortcut some when you know a little bit more linear algebra. Anyway, that's all I want to say on this topic because I think that gives us a nice explanation for what's going on here. So I will stop talking about that, and we'll move on to the last topic we're going to cover in the course, which is a quick treatment of predator-prey models and discrete dynamical systems. So I will see you then.